this video, I will explain on the rules in Diels-Alder reaction, which is an important reaction of cycloaddition. So a cycloaddition reaction of 1,3-diene and an alkene and triple bond, which is called a dienophile, it can form a new 6-membered ring. Dienophile is known as diene-loving, meaning a molecule that loves diene. So in general Diels-Alder reaction, when we have a reaction of Diels-Alder, there are two starting material which is important. The first one is the diene and the second one is the dienophile. Dienophile is diene lover, meaning it will attack the diene. So in this case, the mechanism of cycloaddition reaction proceed this way. So what happened? The pi electron of the dienophile will attack this carbon, and then the electron will migrate to this bond, and the next pi electron will migrate to the other carbon. And then under thermal condition, it will give you a new cycloaddition product. Or we can show when you have a compound which is diene here, and then this is the dienophile. What happens if they form? If they react, they will form a new bond here, and this bond will move to this part. Okay, and what happened? We will get a new pi bond at this region and two new sigma bonds that connect the two molecules together. So in the mechanism of cycloaddition reaction, 3 curved arrows are needed to show the cyclic movement of the electron. Because 3 pi bonds break and 2 new sigma bonds form, and also for 1 new pi bond form. In Diels-Alder reaction, alkyne can also function as dienophile. Other than alkene, alkyne can also function as dienophile. In this case, we react a diene with a dienophile. In this case, is an alkyne. So what we get is a Diels-Alder adduct. Okay, we can draw it this way. Okay, when we have diene like this, so what will happen is we can combine this bond, and then this double bond here will move here, and then what we get is this compound, which is the Diels-Alder adduct. So in general, cycloaddition reaction is a reaction in which two reactants add together in single step to form a cyclic product. So the resulting product must be a cyclic product. Okay, in Diels-Alder cycloaddition reaction, these conditions are suitable for cycloaddition reaction. Okay, let's say we have diene and then we have dienophile. Dienophile, the best condition is when we have electron withdrawing group attached to the dienophile. So when both of these compounds react, it will give us a product with electron withdrawing group. So another condition is where we have diene. So this diene has electron, is attached to electron donating group. Electron donating group. And dienophile contain electron withdrawing group. So in our product, we will have electron donating group at the die-in side and electron withdrawing group at the die-inophile side. Okay, so in das other reaction, there are some examples that we can explore. Okay, if we look at the example here, this is a normal die-in without any particular substituent, and also a dienophile with an aldehyde group. So when it reacts under thermal condition, it will give this new product. And now we have a die-in with electron donating group. So alkyl is a very good electron donating group. Okay, so the dienophile here is having electron withdrawing group. So at the end, we will produce this compound. This is the electron withdrawing group. This is the electron donating group. Now we take a look at the third example. When we have, this is also a die-in containing EDG or electron donating group. And when it reacts under thermal condition, it will give new compound, which is the having electron withdrawing group. So if we look at both all three products, so the red one here are new sigma bond that form after the reaction. Okay, one of the most important Diels-Alder reaction in our natural is that the formation of Tetradotoxin, which is a famous toxin produced by a pufferfish. Okay, so Tetradotoxin is a complex natural product which contains several six members ring joint, and it is a poison which can be isolated from the ovary and liver of the pufferfish. So that's why when there is an enemy, the fish will inflate into a ball, and then if you eat this fish, there will be some trace amount of this toxin which will result in weakness, paralysis, and eventually death. So in the production of tetrodotoxin in Japanese pufferfish body, so one of the important reaction is the Diels-Alder reaction. Okay, when we have, this is the die-in and this is the dienophile. Okay, and then it undergoes Diels-Alder reaction to form this product. So after that, this product will undergo many steps to produce tetrodotoxin. Okay, in Diels-Alder reaction, how do we draw the product of Diels-Alder reaction? Okay, let's say we have both of these starting material. So which one is the die-in, which one is the dienophile? So this is the die-in. So this is the dienophile. So when it is heated, what will be produced? So the first step is we need to rotate the die-in so that it is drawn in the S-cis conformation, and we need to place the NC of the die-in close to the double bond of the enophile. In this case, we have this 1,3 die-in, it is S-trans. So rotate to give us S-cis. So S-cis, and then the dienophile need to be rotate also so that this double bond will meet this double bond. Okay, once we have rearranged the starting material, we can show the movement of electron using the curve arrow. and then we can get this. Those are the product. Okay, in Das-Alder reaction, we have several rules that we need to follow. The first one, the diene can only react when it adopts the S-cis conformation. Okay, this is S-trans. You rotate the molecule so that it will give you S-cis conformer. Okay, once it rotates, only then it can react. If it cannot rotate, it will not react. So this rotation is prevented in cyclic alkenes. So when you have two bonds are constrained to a S-cis conformation, the diene is unusually reactive. And when there are two double bonds are constrained in S-trans conformation, the diene is unreactive. Okay, let's say if we look at this diene is adopting S-cis conformation. When it has S-cis conformation like this diene is very reactive. So it can undergo cycloaddition reaction. But if a molecule having S-trans like this, so this is a very unreactive diene. So this compound will not participate in cycloaddition reaction. Okay, the second rule is electron withdrawing substituent in the dienophile will increase the reaction rate. You remember just now when we had this is the diene and this is the dienophile. Dienophile, for example. Okay, so if dienophile having electron withdrawing group, so the reaction rate will increase greatly. So in Das-Alder reaction, conjugated diene, this diene act as nucleophile and the dienophile act as electrophile. So if we have electron withdrawing group, which is here electron withdrawing group, it will make the dienophile more electrophilic, thus more reactive by withdrawing electron density from the carbon-carbon double bond. So if Z is electron withdrawing group, Z meaning the substituent at the dienophile, substituents at dienophile. So the reactivity of the dienophile will increase as follow, meaning this dienophile does not have any electron withdrawing group. This one has one electron withdrawing group. This one has two electron withdrawing group. So the rate of reaction will increase. Okay, so reaction is facilitated by a combination of electron withdrawing substituent on reactant and electron releasing substituent on the other reactant. Okay, the rules of thumb is EWG must be located at the dienophile to increase the rate of the reaction. Okay, let's say if we look at the first example here, we have 1,3-butadiene. When we react with ethylene, so this ethylene does not have any substituent. Okay, it will give us a cyclohexene. And you look at the condition, it is 200 degrees Celsius and it also needs pressure to carry out this reaction. Okay, now let's have the same 1-butadiene. Okay, now we have a double bond here, dienophile, but the difference between example 1 and example 2 is we add EWG, electron withdrawing group. and when we want to carry out the reaction, we only need to do it at 140 degrees without the use of pressure. So we will get this product. Okay, now let's take a look at example number 3, where we have 2 electron donating group. The alkyl group here, this one does not have any electron donating group, but example 3 we have 2 electron donating group, and then we have 1 here electron withdrawing group. Okay, now let's take a look at the condition of the reaction. You only need 30 degrees Celsius to carry out the reaction. So this shows how important the substituent of the diene and dienophile and how they can affect the rate of the reaction. Okay, another example of electron withdrawing group, yeah. Okay, so a carbonyl group, it is an effective electron withdrawing group because it bears a partial positive charge which can withdraw electron density from the carbon-carbon double bond of the dienophile. Okay, we have the carbonyl here. So this carbonyl, it has partial positive charge. The carbon has partial positive charge, so it can withdraw electron from this double bond of the dienophile, making it electrophilic. So there are some common dienophile as shown in the example here. We have acrolein, we have methyl vinyl ketone, we have methyl acrylate, we have maleic anhydride, and we have also benzoquinone. If you notice that all of the electron withdrawing group contain carbonyl group, as this carbon bears positive charge that can withdraw the electron from the double bond of the dienophile. Okay, so this table summarize electron releasing group and electron withdrawing group. So electron releasing group is also known as electron donating group. So electron donating group are normally comprises of alkyl group, ether or ester, and electron withdrawing group are usually represented by aldehyde, ketone, carboxyl, ester, nitro, and cyano group. So in the next video, we will explain the rest of the rules in Das-Alder reaction.